Okay, hello everyone. My name is Dr. Flash. Now, today's lesson we are going to be talking about dimension. Okay, we all know that dimension is a very important and basic topic in physics. That is why we are going to talk about it. Okay, on the board, I've outlined a few important concepts which we are going to be dealing with. Okay, on the right hand side, we're going to ignore this part first. But on the left hand side, we're having a table. Now, this table contains the primary dimensions, symbols, and units, so I'm going to talk about. Now, first of all, the units here are the SI units for the various quantities on the left hand side. Okay, of course, we should already know by now that various quantities have different way of measuring them, that is, different units. Now, example is force. Force could be measured in pounds or in newtons and the likes, okay, of which the SI units is newtons. Now, here we are having the fundamental 7 quantities we have in physics. We have mass, length, time, temperature, amount of substance, electric current, and then luminous intensity. Now, for the first one, mass, the symbol, we're going to make use of the capital letter M, okay? And the unit is kilogram. Of course, we know mass can be measured in gram, but we're going to make use of just kilogram. Now, the next one here is length. Length, the symbol is capital letter L, and then the unit is M, which is in what? In meters. Over here we have time. Now, time is measured in seconds, that is the unit. But for the symbol, we're going to designate it as the capital letter T. And then for temperature, we're not going to make use of T, okay? Just so that we don't confuse it with time. So we're going to make use of K instead. And then the units could be in degrees Celsius or in kelvins. And then the next one is amount of substance. Now, amount of substance does not really have a dimension, okay? But the symbol is the number of mole. That is where this capital letter N comes from. And the unit is mole, okay? Mole is an abbreviation of molecule. And then over here we have electric currents, okay? Electric current is designated as capital letter I, that is the symbol. And then the unit is in amperes, measured in amperes. And the last one here is luminous intensity. Luminous intensity has the symbol of J, and then the unit is in candela. Now, moving over to this other side of the board, we are having different quantities which we are going to talk about. And basically, we are going to talk about the dimension of these quantities. Now, the first one is acceleration, amount of substance. We have angle, angular acceleration, and the likes. Okay, you can see all of them on the board. But first of all, we need to talk about the methods of getting the dimension of these quantities. And basically, there are 2 methods of doing that. Okay. Now, the first one is by using the unit method. Okay. And then the second one is by using the formula method. Now, for the unit method, basically we just have to know the units of that particular quantity, e.g. acceleration. To get the dimension of acceleration, we just know the units. The unit for acceleration is a very common one. Okay, that's meters per second square. I'm going to show you how to do that. And then for the formula method, we have to know the formula. Okay, that is velocity over time. Now, let's take the first one on the board, which is acceleration. Okay, now acceleration. Okay, for acceleration, let's get the dimension. Getting the dimension for acceleration is very, very easy, okay? And how do we do that? Now, acceleration is velocity over time. That is, A is equal to V over time. That is using the formula method, okay? Now, how about velocity? We don't know the dimension of velocity. We haven't done it yet. Let's assume we do not know it. Now, velocity is displacement over time, okay? And displacement is same as length or distance, okay? Just that displacement simply means traveling length in a particular direction, which makes it a vector quantity. So that is displacement over time divided by the time in the denominator. That is this initial time, of which simplifies to d over t squared. Okay. Now d is distance, okay, of which we said displacement, and they are the same thing. Just that one is a vector, one is a scalar. Now, distance here on the board is length, represents length, okay? And it is represented as a capital letter L. So this can be written as L. And then T is time, which is written as big letter T, that's over T squared. Now, simplify this using the laws of indices. When this one goes to the top, it becomes a -1, okay? That is, the power becomes negative. So this gives us LT minus 2. That is simply how we get the dimension. Now, the other way of getting this is by using the unit. The unit of acceleration is meters per second squared, okay? Now, meters per second squared is written as this, or we can either write it as ms squared, okay? This line simply means per. That is the symbol for division, okay? Now, how do we get the dimension for acceleration using the units? We can as well get it by taking note that meters here is the unit for measuring length, okay, and length is L. So we're going to have, okay, when we have M, we're going to put L. And then when we have S in this case represents seconds, okay, and then for dimension we make use of T, big letter T for time. So we're going to get big letter T. And then for 2, the power is minus 2. So you can see we're actually getting the same answer. LT minus 2 in the first one, LT minus 2 in the second one. Now on the board, I already outlined that amount of substance does not really have a dimension, okay? It is kind of dimensionless. That is why in most quantities you won't find amount of substance in the formula. And then angle, okay? Angle is measured in radians. It is not part of the quantities we have listed here, the 7 fundamental quantities. And of course, there is no dimension. Now, usually we assume the dimension to be 1. Okay, we just assume it to be 1. And then for the next one, we have angular acceleration. Okay, now angular acceleration is the second derivative of angular displacement with respect to time. Okay, that is angular displacement divided by the square of time. Now we can actually write this as theta, okay, divided by t squared for the sake of getting the dimension. Now theta is the unit of theta, which is angle, is radians, okay. But then I said for dimension we take it as 1 because it has no dimension. For that reason we're going to have 1 over t squared, okay. Now time, the dimension for time is capital letter T. That gives us 1 over capital T squared, which is equal to t to the power of minus 2, okay. That is the unit for the dimension for angular acceleration. And then the next one we have angular frequency. Now angular frequency is quite same as angular velocity, okay. Angular frequency, I'm going to write it in brackets as omega. And then for angular velocity, I'm going to write it as a vector quantity, okay. Angular velocity is a vector quantity and angular frequency is not. That's basically the difference. So they should have the same dimension and the same unit. Now the unit for measuring angular frequency is rads per second, okay. Remember, rad has a dimension of 1, so 1 multiplies per second, it gives us per second. Now seconds remains, the dimension for seconds remains big letter T, so that gives us t to the power of minus 1. That's the dimension. So we can actually say that these two guys, they have the same dimension, okay. And then for angular momentum, now angular momentum designated as L, okay. Let me write it in brackets. Angular momentum is L, and it is equal to the product of mass, velocity, and radius, okay. Now mass has a dimension of what? Of capital letter M. So we have M. And then velocity. Now let's get the dimension for velocity, okay. Velocity is equal to displacement over time, and then displacement, the dimension is L because displacement is same as distance, and then the dimension for time is capital letter. So that gives us LT minus 1. So we've done that for velocity, okay. Velocity, okay, the velocity is not among the ones I listed on the board, but here we have it. Velocity is LT minus 1. So I'm going to replace V as LT minus 1. We're going to have LT minus 1. Now radius. Radius is simply what now? Distance. Radius talks about distance, okay, in a circle. Now radius, since we talk about distance, distance is length. So we're going to come back to length. Length has a dimension of what? Of L. That gives us MLT minus 1L. We're not going to stop here. We have to simplify for that. L and L multiplies to give L squared. That becomes L squared T minus 1. So basically here we have the dimension for angular momentum, okay. And then again, angular velocity, we've done it to say it's same as angular frequency. And then area. Now to get the dimension for area, we know that area is equal to length times length. Now, no matter the formula we make use of, whether that of a trapezium, a circle, or a square, at the end, it all falls down to L squared, okay? So we have length times length, okay? Example, for the area of a triangle, it is base times height. Now, this is length, so L times L gives you L squared. The dimension, the formula for calculating area of a circle is pi r squared. R squared is length times length, that is radius times radius, so it all falls down to L squared and the like. So when you do other shapes, you get the same thing. So for this guy, we're going to obtain L squared as the area, okay? Or rather, the L squared becomes the dimension of area. On the board, we also have energy. You could try this one, the same thing, okay? If you want to try these other ones, I would advise you to pause the video and try doing these ones, okay? When you're done, you can play the video and see if you're actually correct. For the next one, we're going to do that of energy. Now, energy is same as work, okay? Energy and work, they are practically the same thing, okay? And work is distance over work is force times distance rather, okay? Work is force times distance. There are other formulas, okay, that relates distance and energy, but for the sake of this one, we're going to make use of force and distance. Now for force, it is mass times acceleration. So we have MAD. I think this is a short way of even remembering the formula of energy, MAD. Okay, mass has an SI unit of kilogram, but we're not talking about the unit in this case. We are going to make use of the dimension directly. Okay, so we're going to make use of M. That gives us M times. Now we've done that of acceleration already. That gave us LT minus 2. LT minus 2, so multiplied by displacement, which is distance. So we have L. Now at the end we get ML squared T minus 2. So basically this is the dimension for energy. Now I also want to try other quantities on the board. Okay, we've done that of energy. Let's now take that of force. Okay, I think it will make it easier if we're making use of the units. Now for that of force, you know that force is mass times acceleration. Force is mass times acceleration. Now initially, I gave two ways of finding the dimension of these quantities on the board, either the units method or the formula method. I'll make use of the formula method. I also want to try and bring in the units method as well, so that to make things easy, okay? At least doing them side by side should make you understand this better. Now for force, we can actually make use of the formula, the units method or the formula method. Now first of all, let's make use of the formula method. Force is equal to mass times acceleration. Okay, now to make things easy, M has a dimension of capital letter M, okay, and acceleration has a dimension of LT minus 2. So I'm going to just multiply by LT minus 2, okay, so that gives us MLT minus 2. So basically this is the dimension for force. Okay, now let's make use of the units method. Using the units method, we already know that the derived unit of force is kilogram meters per second squared. Okay, so knowing that the derived unit of force is kilogram meters per second squared, we won't be needing the formula, which is mass times acceleration. Now kilogram has a dimensional unit of capital letter M, same as M. Okay, now M has a dimensional unit of L. Okay, because M here does not represent mass, it represents distance or length, and then S here represents time. So we have MLT minus 2. That is how we work it out basically. So for force, we've done that of force, okay? We've done that of force, energy, area, and the ones above it. Now the next one is heat. Heat is also same as energy, of which we've done energy. Okay, so I'm going to write it. Heat is same as energy. Okay, heat is same as energy, which is also same as work done. So basically these three guys, they have the same units, okay, in terms of dimension. So heat is same as work done, okay, and it is same as energy. So basically these three guys, they have the same dimensional formula. Now the next one on the board is volume. Okay, now we already know that volume always have a unit or an SI unit of meter cube. Okay, of course it could be measured in decimeter cube, liters, and other form. Okay, but we're going to make use of meter cube. This time around we're using the units method. Now for meter cube, we know that meter simply means length, and then from the table I gave initially, okay, if you don't have the table noted somewhere, you can actually rewind the video and get it. It's on the it was on this part of the board when we started the video. Okay, so M cube is the unit for measuring volume, and then M is represented as L in terms of dimension. So I'm just going to have L cube. Okay, this gives us the dimension for volume. L cube gives us the dimension for volume. And then the next one on the board is power. We have power, period, pressure, density, speed, torque, momentum, moment, stress, and strain. Okay, we've not done all of this. Now let's take the next one, which is power. Now first of all, What is power? Power is the rate at which work is done, that is work over time. Now, to make things easy, let's fall back to the unit method. Okay, from the unit method, we've done the dimension for work. Okay, the dimension for work. And we can get the dimension for work from MA, which is same as energy. Okay, that is ml squared t minus 2. So I'm just going to repeat it. ml squared t minus 2 divided by time. Now time is t. So when we do the math, we're going to take that guy upward. That gives us power equals ml squared t minus 2 times, take this guy, so we get t minus 1. Now simplifying this using the laws of indices, we get ml squared, okay, t. Now minus 2 minus 1 is minus 3. So this is the dimension for power. And then the next one on the board is period. Now what is period? Period is the number of oscillations or cycles or revolution performed in a given second, okay, in 1 second or in a given amount of time. So period, which is represented as capital letter T as its unit, or its symbols rather, capital letter T, is numbers of oscillations over time. Now number of oscillations is like just a number, okay, or just counting the number of cycles being created. It does not have a dimension. So we can also as well assign a dimension of 1, okay, to it. So we have 1 over t. Now t here is time. Okay, let me just small letter t. T here is time. And then the dimension for time is capital letter T. So when I take this upward, it gives us t minus 1. So basically, this is the dimension for period, okay? So we've done that of power, that of period. Let's now do that of pressure, okay? Pressure. Now pressure is force over area. Pressure is force over area. Now what is the dimension for force? So done force as well is on the board. mLT minus 2. mLT minus 2. And then area is L square, of which we've done it already. Okay, I think we've done area. Area is L squared. Okay, it is here. Area is L squared. So now when I take this upward, of course, one L cancels out one L in the bottom. So this L remains L to the power of 1, which when we take it upward becomes ml minus 1 t minus 2. Now please take note that the format is usually m followed by l followed by t, okay, then followed by any other one quantities like temperatures, okay. Remember I gave you 7 on the board. So the basic one is m, l and t, okay, followed by every other one. So if you're writing the dimension, it should be in this format: m, which is mass, followed by length, followed by time, and then followed by temperature, okay, and then points. Because in most exams that you find in O level, they usually take this format: MLT, okay, that's the format they usually take. Now we've done that of pressure. The next one on the board is density, okay, density. Now from the formula, density is mass over volume. Density is mass over volume. Now what is mass? The dimension for mass, it is capital letter M. It is not changing. And then volume we've done it, that is LQ. That gives us ml minus 3. And we can also get it using the unit method, okay, depending on which one works best for you. Now using the unit method, you know that density has a general unit of kilogram meter cube, okay, kilogram per meter cube. Now kilogram represents mass, of which from the table I give, mass has a dimension of capital letter M, okay, and then meter, which is M, has a dimension of L. I think the most confusing part of this topic dimension is the fact that most students cannot differentiate the difference between kilogram or makers of M and then length or makers of M. Now take note, it's very easy. When using units, okay, when using units, mass should be kilogram and length should be meters in small letter. But when using dimension, mass should be capital letter M, and then meters, which is distance, should be capital letter L, okay. That's the difference basically, okay. Now let's move on to the next one. The next one on the board is speed. Now speed is actually a scalar quantity while velocity is a vector quantity. They have the same dimension. The only difference is that one is a scalar and then one is a vector, okay. That's the difference between speed and velocity. Now for speed, I'm going to do it up here. Speed is distance over time. Distance has the dimension of L time has a dimension of capital letter T, so that gives us LT minus 1. Okay, so we have done that of volume. Okay, I think I wrote volume twice. So I'm going to take out this one. We've done density, we've done speed. Okay, now the next one on the board is torque. Okay, let's take that of torque. Now torque is force times perpendicular distance. Okay, imagine we are having a lever like this. Okay, and then a force is applied at one end. We are asked to find the torque about this center point. We are going to take the distance, which should be d over 2. That is, if the total length of the lever is d. Okay, let's say we apply a force. So torque, which is represented as tau. Okay, this is the symbol for torque. It is force times distance. Okay, force times perpendicular distance actually. So even if we're having a force that is acting at an angle, we must have to resolve it. Okay, to make it vertical, so that we can make it perpendicular. So basically, torque, which is represented as tau, is force times perpendicular distance. This symbol means perpendicular. So force times perpendicular distance. But then again, take note that there are some certain things that should never show up when dealing with dimension. Now, example is symbols like this. Okay, symbols like this, which tells us that it is perpendicular, should not show up. Now, constant too should not show up when dealing with dimension. Take note, constants like pi should not show up. Okay, even if the formula contains pi, it should not show up. Now, another thing again is another Greek symbol, which is delta. Delta, change should not show up. Now, remember when we did angular acceleration, we had this symbol. Delta simply means differentiate, it means d. Remember, angular acceleration was second derivative of angular displacement with respect to time. Now, this d is same as delta. We can also write it as second derivative with respect to time. Okay, so this guy should not show up. That was why I had to eliminate this guy and write it as theta over t squared. So basically, that is what we do when dealing with dimension. Okay, now we've done that of torque. Let's now move on to that of momentum. Let's move on to that of momentum. Okay, now this is for torque. Okay, we've not even done that of torque. Now, for force, we had mlt minus 2. Okay, that is mass times acceleration, and then distance is L. This perpendicular should not be involved. So this is m. Okay, this is m. L times L is L squared, and then we'll have t minus 2. So that's for torque. And then the next one on the board is momentum. Now, momentum is mass times velocity, and mass is capital letter M. Velocity is LT minus 1. So that gives us MLT minus 1. Okay, and then the next one is moment. Okay, we already know that moment is the turning force of a force above a point, and it has the same formula as torque. Okay, so moment is force times distance as well. Okay, now moment is same as torque actually. Okay, I don't even know why I placed it there twice. So that will give us the same units as torque, which is ml squared t minus 2. Now we are done with these first few ones, and then we are left with stress, strain, and Young modulus. Now, to get out of stress, strain, and Young modulus, it is important to know the units of these guys. Okay, now what is the unit of stress? What is the unit of strain? Okay, now if you know that before I want to think about it, you can pause the video, think about it, play the video, and then you'll find out what your answer is. Now, for strain, first of all, there is a relationship between stress, strain, and Young modulus. Okay, that's one thing you should know. You should know that Young modulus is stress over strain. Now, for strain is extension over original length. Imagine we are having a rubber band like this, okay, of let's say perimeter 20 meters, and then it is stressed such that the perimeter becomes twice of the initial one. Okay, let me make it bigger to show that it's actually twice. Okay, twice of the initial one. That is, the distance around this circle is 20 meters initially, and it is stretched such that the new length becomes 40 meters. That is new perimeter. Now, what will be the extension? By how much does it extend or stretch? It will be the difference between these two numbers. That is 40 minus 20, which gives us 20. So the extension is 20. Okay, it must not necessarily be twice. Imagine it is stretched so that it becomes 5 times longer. The extension is 5, and then the original length is L. Now, extension is also measured in distance. Okay, that is length. and length remains length. Okay, it's also measured in meters. So when we have both quantities measured in meters, they both cancel out and they give us the measure of what now? Of 1. Now for stress, stress is simply tangential force, okay? Tangential force over area. Okay? Tangential force over area. Now this tangential doesn't really do anything, it just tell you how the force is acting on the body, okay? Now we are going to ignore the tangential when dealing with the dimension. So for the sake of dimension, we are going to have just force over area. Now we've done force over area before. If you recall, there is a quantity that has a formula of force over area, okay? Ignoring the tangential in this case, it has force over area, and I think that is pressure. If pressure has force over area, stress has force over area, it simply means they're both going to have the same dimension, okay? Now, in this case, the same dimension on the same unit. In this case, pressure gives us ml minus 1, T minus 2. So I can simply come here and write ml minus 1, T minus 2, okay, as the dimension for calculating stress. And then the last one on the list, we have Young's modulus. Young's modulus. I've given the formula on the board already. It is ratio of stress to strain. Okay. Now stress has a dimension of ml minus 1, T minus 2, and then strain has the dimension of 1. So I'm going to divide by 1. Dividing any quantity by 1 gives us that same quantity. So obviously the dimension remains ml minus 1, T minus 2. Now what do we notice amongst all the dimensions I've talked about? Young's modulus, take note, Young's modulus, stress, and then pressure, they have the same dimensional quantity. Okay, so it is very important that you take note that Young's modulus, stress, and pressure have the same dimensional quantity. Now there are other quantities I put on the board that we notice they have the same dimensional quantity. One of them is torque. Okay, one of them is torque followed by moment. One of them is torque followed by moment, and I think I've done moment already. Moment is also force times perpendicular distance. Okay, here we have moment. Okay, and then it is same as energy, because energy is same as one, which is force times distance. The only difference is that for moment and torque we are having perpendicular distances. Okay, so energy, moment, and torque, they have the same dimensional formula. Okay, using the formulas that I gave you. Now I hope you guys will understand how we work out different dimensional quantities using formula method and the units method. Of course, there are other quantities we can talk about. Okay, there are other quantities we can talk about getting their dimension. Now I'll leave that to you guys. Okay, if you know you can try them out, just drop the answers in the comment section. I'll leave that to you guys. Just drop the answers in the comment section. Now the first one I'm going to take here is moments of inertia. Moments of inertia. Okay, you can try them out and drop it in the comment section. And then the next one I'm going to talk about is let's see the one that is not on the board. Okay, I think I did not talk about impulse. Okay, I did not talk about impulse. And then we still did not talk about entropy. We still didn't talk about entropy. And then let's say resistance. So basically we have 4 quantities that I would like you guys to try out here. Okay, try out these 4 quantities and drop your answers in the comment section. Let's see how well you've understood this concept of dimension. Now my name remains Dr. Flash. Do well to subscribe to this YouTube channel. The name is Dr. Flash, and then click on the notification bell so that when a new video is being uploaded you will get it. Okay, now do not forget to like the video as well, and then share it to your friends and colleagues. Okay, do not let them know, make sure your friends are learning with you. Thank you for following Dr. Flash on YouTube. Of course I know you will. Okay, see you in the next video.